Hello, welcome again. Today we start a new section on the time response of systems. In general, when we apply an input to a system, the response, the output response, is affected by two, two things. It is affected by what kind of the forcing function we use, like a step input, sinusoidal input, a ramp input, and it also depends on the natural characteristics of the system, which is basically by the system model or the transfer function. Usually, when we look at the output response, we can look in the time domain, and we can see two distinct characteristics. We can see a transient response. So here the output response will vary significantly. And this mode is going to decay over some time. So this depends on the system's natural characteristics. So the system's natural response decays after some time. And then it settles down into the steady state response, which is mainly just affected by the forcing function. We are using we are interested in control systems. So when we design a control system, we want to get a certain specific performance out of the closed loop system. So if we are going to be designing closed loop systems in order to have a certain performance specification, we need to be able to come up and define mathematical quantities that describe both the transient of the response as well as the steady state response. In order to come up with these mathematical quantities, we'll describe quantities like settling time, rise time, percentage overshoot. We will also look at how much is the steady state error of a system with respect to a reference. We want to be able to relate the steady state error to the characteristics of the system model, which is the type number, which we will look later on in the subsequent flip lectures. We want to be able to do this. We want to analytically understand it for a variety of simple systems like the first order and second order systems. So first order and second order systems are basically when the transfer function has the highest power of s as 1 or 2 respectively in the denominator. So the highest, so a transfer function gs can be written as a polynomial numerator divided by a polynomial denominator. So a first order system will be when the highest power of s in the denominator is 1. The second order system is when the highest power of s in ds in the denominator is equal to 2. We will also be relating later on how for the first order system and the second order system, the time response depends on the pole locations of the S-plane. So let's try to understand, first of all, what kind of response we are studying. In general, I can apply any arbitrary input to a system, and the output will vary according to whatever kind of input I've applied. For a practical system, it is not feasible that I keep on applying arbitrary inputs and keep on testing, looking at the output for any arbitrary inputs. We usually use certain benchmark or test signals. So these benchmark signals or the test signals are the ones that we have already described the Laplace transform for. So we looked at impulse, we looked at earlier at Laplace transform of impulse, step input, ramp input, and parabolic input. We also mentioned that we can consider a unit input, which is basically having a magnitude of 1 in some sense, as for impulse input when the area under the Dirac delta function is equal to 1. For a step input, we consider a unit step input when for time t greater than 0, we have a value 1. For a ramp input, we consider the unit step function, unit step ramp, when the input is t, and basically we just have a coefficient of 1. So it basically translates to having a slope of the ramp function as 1. The parabolic similarly is the unit function is t squared, so it has a coefficient of 1 associated with it. And we have looked at it that these are the different different Laplace transforms corresponding to it. Let's look at the different response specifications, which are basically the measurable quantities that we will describe of how a system responds. So in order to look at these measurable quantities, we can possibly get two general responses. We can get either a monotonically increasing, so we apply, let's say, consider a step input. One possible response is that the output monotonically increases and reaches a second uh, steady state condition. Or the other possibility is, so the first case that I described is the monotonic increase. The second case is when the output starts out, it reaches the second steady state, but it does not stop over there. It rises further, reaches some peak value, which basically the difference is the overshoot from the steady state value. And then it approaches the steady state again, can undershoot. It does it a few times, and then it settles down within some narrow band, or finally, as time t tends towards infinity, it reaches the steady state condition. So both these responses, I use the step input as a standard test signal in order to describe these two kind of responses. And I'm going to be describing the uh, response specifications for these for a step input as a standard test signal. So we could be uh, qualitatively, we could be interested in how fast the system is responding, which is like how fast is the speed. You could also say like what is the speed of response. Alternatively, another qualitative thing is that how well have I been able to track my reference, or how close am I to my reference signal, which is the closeness of the response. So these response specifications that I described, you can consider that they are either looking at how fast the system is responding, or how close I am to the reference signal, or what is my error in the response. So let's look at the speed of the response. So the speed of the response, uh, we have, or swiftness of the response, we have basically these three specifications which are commonly used. The settling time is the time that it takes, that the system takes in order to settle down within a certain percentage of the steady state value. We often use 2%, sometimes we also use 5% of the steady state value. So if I'm settling down at YSS, 2% band will be when I am between 0.98 YSS to 1.02 YSS. So similarly for the oscillatory response, when I am within this band, so once I reach within this band and I do not go out of this band, I basically reach the steady state value, which happens at a point over here for this case. Similarly, if I was talking about a 5% band, the 5% band will basically mean that I am between 0.95 YSS to 1.05 of the steady state value, YSS. The rise time is the time it takes to go from 0 to 100% of the steady state value. So the time that my response takes to go from the very start to the steady state value, but it doesn't settle over there. It can overshoot, so it can still have a lot of oscillatory response. So for the oscillatory response, it takes, this is basically from the start till the time that I take to reach the YSS value. However, notice that this definition is not valid for a monotonically increasing response. So in this case, I only reach the steady state value at time t approaching infinity. So in this case, for a monotonically increasing response, I use the definition that my rise time is the time it takes from 10% to 90% of the steady state value. Peak time is a time that it takes to reach the maximum value of the response. So peak time is the time that it takes to reach the maximum value. Peak time is not valid for a uh, monotonically increasing output response. For closeness of the response to a reference signal, we use the definition. We have a performance characteristic, which is the steady state error. So a steady state error is basically the error between the desired value and the actual value at time t equal to infinity. So this is basically same as what is the desired value, which if I'm just using a step input, it is a constant value. So if I use a unit step, it will be the desired value. Uh, uh, if I apply a unit step to a closed loop system, then the desired value will be equal to 1. Uh, and the steady state value will be whatever is the output of a closed loop system at time t equal to infinity. Then we also have other measures like the peak value or the peak response, which is basically just the MP, which is the maximum value that the output can take. Or it could be expressed as a percentage overshoot, in which case I am looking at overshoot minus the steady state value. So the difference of the overshoot from the steady state value divided by the steady state value. So if I multiply this with 100, I'll end up getting the percentage overshoot. So this completes the different time response specifications that we will be discussing in this paper mainly. Thank you.